Good morning, ladies and gentlemen, and welcome to this WTW218 questions and answer session. This is going to depend very much on on you guys. I will accommodate questions from your side. I'm not going to do any overviews or represent some of the material that we've covered already. So when you're ready, you can either unmute your mic. I'm not sure if that facility is available to you, and then post your question, or you can use the chat facility to post your questions there. You will probably be referring to our course notes and the exercises in that. Or if it's another problem, then you'll have to find a way to explain to us what the problem is. I see there are still a number of people joining us. At this stage, we're just more than 30 students that have joined the session. So, yeah, if you have questions, you're ready to start posting your questions. Thank you. Okay, I'm not sure whether you can all see the chats, but we have some questions on exercise 5.5. And the first one is number 1E, where we have to find the value of a double integral of the given function over a region by using polar coordinates. Now, in 1E, the function is very simple. So the function that we have here is just f at x, y equals 1. That's a constant function. Okay, that's quite easy. The region is a bit more complicated. The region D is described as follows. Inside, oh, that's not good. Inside a circle with equation x squared plus y squared equals 4. That's not so difficult to understand. But then also outside, ooh, I can't spell outside like that. Spell it like that. Outside another circle with equation x squared plus y squared equals 2x. Okay, so where lies the problem here? The problem lies in understanding this second circle that you have here. And the way to understand that second circle is by simply just completing the square in x. So I'm going to write with a pencil, and I know it's not a very great way to read it, but in any case, so you take the 2x over to this side, okay, and I'm going to add 1 so that I can complete the square. You remember how that works? You take half of the coefficient of x and you square it, okay? So from that second equation, you're going to get this. In other words, if you factorize this expression here, you're going to get this. x minus 1 squared plus y squared is equal to 1. Okay, now you can begin imagining what the region D looks like. So we've got this situation in the xy plane. We've got a circle with radius 2 about the origin. So that's quite simple. There's our one circle. Oof, doesn't look like a circle, but you know what I'm trying to do, eh? So there's a circle with radius 2, okay? And this other circle of us has as its origin the point where x is 1 and y is 0. X is 1 and y is 0, and the radius is 1. So that's your other circle there. So the region D that we're looking at is this region here. Okay, that's D. It's inside the bigger circle, outside of the smaller circle. Okay, and you have to use polar coordinates, so you have to find a range for theta, and you have to find a range for the radius r. Okay, so maybe if we just look at that first equation and substitute, remember for polar coordinates, x is r cos theta and y is r sin theta. If you look at this equation here, and you translate that into polar, you're going to get r squared is 2r cos theta. Hope that's clear to everybody. Okay, and from that you can deduce r is not 0, you can divide by r and you get r equals 2 cos theta. Oof. It's not easy for me to write with this map. Okay, so r is 2 cos theta. That's the equation in polar coordinates of this smaller circle here. Okay, now let's think about theta. Where does theta have to start? E. Maybe it's easier to just say where r must start. R must start from the inner circle, and it must move up to the outer circle. So you can see that r has to be between 2 cos theta and the bigger circle, which has a radius of 2. Okay. Theta is measured from the positive side of the x-axis. So theta will start at 0 because that's where these two circles actually intersect. Okay. Theta will start at 0. And theta has to go all the way around up to 2 pi. Okay, let me just see something quickly. Come on. This thing is super slow. Dr. Wortel, are you there? You must please chip in if I'm talking nonsense. Okay. Right, I think with the information that we have here now, you should all be able to do the integral. You need to find a double integral over the region D using polar coordinates, and the function is just fxy equals 1. So your integral will look like this. Your answer needs to look like this as a iterated integral.
Can I make a comment?
Yes, please do, Dr. Wortel.
So, so there's another little thing. Isn't that on the left hand side? Let me also try. Yeah, I'm also not on my tablet. Uh, on the left hand side, we just have r from 0 to 2. So let's do it with a red line. So we can split it up into two regions. Basically, the left hand side region, where we just have the radius r from 0 to 2. But on the right hand side, we have different behavior. So let's maybe do that in purple. So on the right hand side, we have precisely what Dr. Olaf is saying. So in purple, we have that r is between. Apologies, I'm also not on my tablet. R is between 2 and 2 cos theta. Right? We can see that from the picture. Whereas on the left hand side, we have different behavior because there's no inner circle, uh, does not affect the region. So in this region, we simply have r from 0 to 2. So the important step here is that you also, this difficult exercise where you have to recognize that you have two different behaviors. And then there's a theorem in the book that tells you that if you have, you can always split up your integral in one piece, you can split up your region into two pieces and you just add the integrals. So first you do the red integral, which is going to look like this. So that will be the integral from r from 0 to 2, and then theta from, maybe try that yourself. So what are the ranges for theta for the red region, and then the function 1, of course, then there's the Jacobian r d theta. So that's the red region, and then you have to add the purple region, in which, again, figure out the bounds for theta for the purple region, and there the radius is from 2 cos theta to 2 of 1, and again, we have the r from the polar coordinate, the r d theta. Okay, so yeah, so that was my comment. I see that Dr. Olof's connection is very bad at the moment. So are there any questions about this? So the difficult part of this exercise, well, there's multiple difficult parts. Let me just go over them. So first thing is that you have to realize how to write this as a circle, the way Dr. Olof did it. And then you have to sketch the region, and then the second difficult part is where you have to realize that there is different behavior in certain parts. So we have the red part where we the radius is just from 0 to 2, and the purple part you can see in the picture. Maybe I should try to explain this. If I draw a line from the origin to the boundary, I see that it starts in the inner circle and it ends at the outer circle. And so therefore, for the outer circle we have r is 2, and for the inner circle, as done here by Dr. Olof, we see that the r value is equal to 2 cos theta. Okay, so and then all that you have to do is to find the correct bounds for theta here, but yeah, you should be able to do this, right? Find the correct bounds in the purple region for theta and in the red region for theta.
Okay.
Okay,
Is my
are you back?
connection better now?
Yeah. No,
Is my
you
is
were. It's good now. We can hear it.
okay. Okay. So if I have a look at the chats, uh,
Oh, it seems your connection has again dropped a bit. It's back now. So Thomas, the purple region is minus pi over 2 to pi over 2. Yeah, that's correct, because yeah, so the bottom one is over here, and then you go all the way around, right? This is minus pi over 2 up to pi over 2. And for the red region, we have pi over 2 to 3 pi over 2. Right, and remember, you can see there are these answers to the exercises. They're not complete answers, but there you can actually see the two different integrals. Remember, on ClickUp, there's a tab called Answers Hints to Exercise in the course notes, and then you can see that there's these two integrals, which correspond exactly to the red and the purple region. Okay, I'm not sure if Dr. Olaf seems to be having connection problems, so maybe I'll just continue. Are there any further questions about this exercise 1E of 5.5? Okay, I will then clear the screen, and we'll continue with the next question, which is 2B. Okay, so what is the question? Draw the region for exercise 5.52B. Okay. Okay, so there again we have inside the circle with equation x squared plus y squared plus 1 it equals 1. Let me write this. So inside this circle, well, okay, that's easy. That's just a circle with radius 1. And then we have below the parabola with equation y equals minus 2 root 3 x squared. Okay, so minus x squared would be a parabola going down, but there's the minus 2 root 3, so it will be going like this, right? It's very ugly. Okay. So it's below there, so it's going to be, let's draw the region in red. It will be over here, right? That's our region D. Are you with me so far, Olivia? You asked this question. And are there any other questions so far? Okay. So it says the fourth quadrant. Oh, the region in the fourth quadrant. Okay. Sorry. Yeah, I missed that. Oh, all with white. So this part is not there. So it's only in the fourth quadrant, so it's only over there. Okay, so now yeah, how shall I? Okay, so let me try to read. So remember this line here is tangent to the x-axis. So I'm trying to redraw it a little bit so that it's more clear. Okay, and we have an intersection point over here, right? Okay, the question is how to get the bounds. Okay, well this question is actually quite similar as the previous one. And the thing again is that we have different behaviors in some parts. So let me indicate this with a blue line. So I have my blue line over here, right? So I've got the stuff below the blue line and the stuff above the blue line. So below the blue line, I can see that, yeah, okay, so maybe I should make this a blue region and a purple region again. Yeah, so everything is in the fourth quadrant, right? So it's only in the in that bottom right block. And I see that in the blue region, yeah, so let's do that in blue. I can see that the radius is simply from 0 to 1. Right, because I start, let's just draw a random line in the blue region like this. You see that the entire line is contained in the red area. So in the blue region, we have that the radius goes from 0 to 1. Now, however, in the purple region, it's different. So let's draw an orange line in the purple region. You see, in the purple region, we actually start at the origin, but we stop not at 1, but we stop at when we hit this curve over here. Yeah, so the orange region is going to be 0 is less or equal than r is less or equal than, and then a question mark. Yeah. So in the orange region, we hit when we the question mark is related to this equation where y equals minus 2 root 3 x squared. So this is how we should get the bounds for r in the purple region. Okay, so maybe let's compute this. So as before, we know that y. So how do we get the bounds for r? Well, we simply take y and x and substitute the polar coordinates, right? So y is equal to r sine theta, and x is equal to r squared. X is equal to r cos theta. Okay, so now we want to find the bounds for r, so we want to isolate r, so we can divide by r, and then we need to divide by cos theta, so we have sine theta over cos theta, and we also need to divide by 2 root 3, and this is where we are equal to r, right? So, and that sine over cos is the tangent, so we have tangent theta over 2 root 3. Yeah, so that is how we compute this question mark. So this is apparently equal to tangent theta over 2 root 3. Okay, let me stop for a second and ask if there are any questions about this computation for the bounds for r in the purple region, or any other questions so far about the exercise.
Dr. Wortel, I've rejoined. I just want to make sure if you can hear me now.
Yeah, I can hear you.
Okay, just a comment. I think the negative sign disappeared in the final equation there.
Oh yeah, there's some mistakes. Someone said the cos theta means to be squared. Yeah, that's correct. So this should have been a square. So this should have been a square. Okay, so and also the negative sign has disappeared. So there should be another negative sign. So this is actually incorrect. So this should be, I think it should be sine over minus 2 root 3 cos squared. Which you could also write as like the tangent times the secant, right? The sine over cos squared is the same as the tangent times the secant. Okay, so I made some calculation errors. I think it's correct now. Is it correct now? Can I get some confirmation or?
Yes, correct.
Okay, any other questions about this part? About this is purely computing the upper bounds for r. Yeah, so now we have to think about theta. So as I said before, there's two different behaviors. So first, what we need to do, okay, so what are the bounds for theta? Well, we see that in the fourth quadrant, and we also see that, yeah, I could draw another orange line here. If I get very close to 0 here for theta, I still have parts in that parabola, right? Because the tangent of the parabola is 0 at the origin. So I can see here that in the purple part, I can see that theta goes from the upper bound of theta is 0, and the lower bound of theta, that is this mystery angle, which I will call with a question mark. That is the angle that corresponds to the blue line. So let me just put a question mark for there. So what about the bounds for the blue region? Well, there we have that theta will start at it starts over here, right, in the negative y direction, which corresponds to the angle minus pi over 2. And then the upper bound will be with that same question mark angle. Yeah, so is that clear? That's okay. Are there any questions about the fact that the purple region is from question mark to 0 and the blue region is from minus pi over 2 to question mark? Are there any questions about that? Okay, so all that remains is to find, right? I think you all can now finish the question because again you have to split it up into the sum of two integrals. So all that remains is to find the question mark angle. And how do we do this? Well, let's look at our picture. We have our intersection point over here, right? So if we can find the coordinates of the intersection point, we can find the angle theta that belongs to that intersection point. So how do we find the coordinates of the intersection point? So let's do that in black. Well, in the intersection point, I have two equations that are satisfied. X squared plus y squared is 1. And I have the equation where y equals minus 2 root 3 x squared. Okay, so now I just have to solve these two equations simultaneously. So for instance, what I could do is, what would be the easiest? Probably to substitute x squared is y divided by, so we can substitute x squared is y divided by minus 2 root 3. And then I add y squared, and then it must be equal to 1. Right, and then I can solve this for y, and once I have y, I can find the corresponding x by plugging it in one of these two equations. Right, so what I'm doing is solving these simultaneously. Yeah, then I have my point. Once I have my point, I can find my angle, and then I have solved the exercise because then I have everything that I need. Okay, but let me not do this. I think you can do this yourself. So, are there any questions about the procedure? So maybe do this exercise again after this session and see if you can complete the exercise yourself.
Thank you very much, Dr. Wortel, for standing in there. Since I had to go out and come back, I have lost the chats, so I don't know what the other questions were. Can I ask the
Okay.
students to just please repeat them, or if you can just tell me which one we should do next?
Yeah, so there's one more question from Olivia. Tangent theta is m to find the angle. Yeah, that's fine. But if you have a point on the unit circle, you should know how to find the angle, right? You can use that or simply draw a local triangle or but that's also, yeah, you can use the slope is the tangent. I think that's correct. So that's fine. Okay, I'm gonna relog and log in with my tablet so I can write a bit better if necessary.
Okay. See
Okay, I can see that
Put
Dr.
the
Olaf
math
has some
work.
audio issues again.
Ah, near.
No, okay, yeah,
Can
we
you
can
not
hear you
hear
now.
me?
Yeah, it's fixed now, I think. But I think what you've said so far has not
It
been.
comes.
Oh, it's connection is bad again.
Sorry, I've lost you now.
Yeah,
Okay.
I can hear you now, I think.
Um,
But your connection still looks
okay, but
as.
I see many of the students are complaining.
Yeah,
Yeah,
it's
okay. I'm
maybe
going to
explain it
restart
again.
my computer.
No, I don't think that
Okay, so
matters.
what I'm saying here is, can you hear me now?
We can hear you now.
No. Okay, so I'm saying to prove that this limit is equal to 1, you have to work with this expression, the absolute value of the difference between e to the 2x squared plus 3y squared minus 1. And it's difficult to use that expression directly as it is. But if you look at the normal exponential function, you can see that x is always less than e to the x. So you can, in this instance, you can see that you can write 2 times e to the x squared plus 3 times yx squared. Man, this writing is not easy. That's always less than e to the 2x squared plus 3y squared. Are you all following that? That's just a basic property of the exponential function. Now you can subtract minus 1 on both sides, and actually from there on you should be able to do this problem on your own. That is a basic, if you want to call it a trick, that you need to be able to solve this, to prove this limit. Is that clear to everybody?
Okay, Dr. Olaf has problems, so he's going to restart. So I think I'm going to do this. I will do this, but I'm going to use a different method. So let me explain how I would do it. So let me clear the screen. So again, we have the limit for xy to the origin of what if we e to the power 2x squared plus 3y squared is equal to 1. Is that the exercise? I believe it is. Okay, so yeah, there are some hints given in the solutions on ClickUp. So I will follow this the idea. So first, so so the idea is as follows. So first look at e to the power 2x squared plus 3y squared minus 1, and we look at its absolute value, right? This is always what you want to do. We take the function and we subtract the limits, and we try to estimate this. Okay, so the first thing that's given is that this is equal to the same thing, but without the absolute values. So my question to you is why is this equality true? Why can we get rid of the absolute values here? So note here I'm following the solution on ClickUp that you can find in the tab answers/hints to exercise in the course notes. So can anyone tell me why is this? Yeah. So okay. So there are some good remarks in the chat. So the first remark here is that the orange part, the exponent, is positive, right? It's not negative. Yeah. And furthermore, we know that e to the t is bigger or equal than 1 for t positive, right? Just look at quickly the graph. This is 1. So if t is positive, e to the t is bigger or equal than 1. So it follows that this thing is bigger or equal than 1. And then I subtract 1, and therefore it follows that the entire expression, the purple expression, is positive. Because I have something that's bigger or equal than 1, and I subtract 1. And that's the thing in the absolute values, and the absolute value of something positive is the thing itself. So this is the reason why we can get rid of the absolute value. Okay, let me know if there are questions about this step. Okay, and then the next step is, then we say, well, this is actually less or equal than e to the power 3x squared plus 3y squared minus 1. This is again because of the same reason. Yeah, so let me not ask you, but if we compare the two orange parts, we see that 2x squared plus 3y squared is less or equal than 3x squared plus 3y squared. Yeah, and if we look at the orange graph of the exponential function, if we have 2 points s and t, we see that e to the s is less than e to the t if s is less than t. So if I increase the exponent of the exponential function, the value is bigger, and this is why we have this less or equal. Yeah, this is a bigger thing because the exponent is increased, and then since the exponential function is increasing, the exponential function will get bigger as well. Okay, any questions about that step? Okay, so now let's continue over here. Remember, the goal of what we're trying to do is we're trying to estimate this thing over here by something which is a function of the distance from xy to the origin. We need to estimate it by the distance from xy to the origin. And here we have that. We have 3 times that. 3 times that squared. So we can write this as e times 3 times the distance of xy to the origin squared. And we still have our minus 1. Yeah? This is because I can write it as 3 times and then x squared plus y squared. And that's precisely the distance of the vector xy to the origin. Okay. So now once we're at this step, okay, so the way that I explained this in my lectures, other lectures may have done this differently, but you should be able to do this. We know that this distance is going to be less than. Oh, I should
should do it like this. This distance is going to be less than delta eventually. So it follows that this is going to be less than e to the power 3 delta squared minus 1. Right? Once we choose our delta and we choose our point x, y such that the distance to the origin is less than delta, we can get that this is now less than e to the power 3 delta squared minus 1. So now we need to figure out what our delta should be given our epsilon. So what we want, we would like this to be less than equal to epsilon, or less than epsilon, because then we are in business, because then this thing is going to be less than epsilon. So this is what we want. And now, to get what we want, we just have to solve this equation that we have over here. Yeah. So to get what we want, maybe let's do that in a different color, purple. So we want this, and how do we get that? We solve the equation where e to the power 3 delta squared minus 1 is equal to epsilon. So how do we solve it? We want to solve it for delta. Remember, we need to say what delta is in order to solve this exercise. So how do we do this? Well, we want to solve for delta, so we want to get rid of everything else. So we get e to the power 3 delta squared is epsilon plus 1. Okay, so now I need to get rid of the e, so I should take logarithms. So I have that the log of, take logarithm both sides will give me 3 delta squared is the log of epsilon plus 1. And then this will give me that for the positive solution, delta is going to be the square root of log of epsilon plus 1 over 3. Yeah, so this is, in this solution, this is where the delta, right, this is written in the solution, but this is where it comes from. It comes from solving this equation over here, where e to the power 3 delta squared minus 1 should be equal to epsilon. Note that all of this makes sense because epsilon is positive, so epsilon plus 1 is bigger than 1. And therefore, the log of something that's bigger than 1 is going to be bigger than 0. So this is actually positive, and therefore I can take the square root. So all of this makes sense. Okay. So any questions about this part so far? So how to get the delta? So this is quite a tricky exercise because there's a lot of steps, right? You start off with this, then you need to recognize that it's always non-negative, so you can take away the absolute values. Then you have to do some clever estimates where, well, we get 3x squared plus 3y squared, and then at the end you still have to see the fact that you can get your delta by solving this equation over here. Normally we get quite easy things like 3 delta squared equal to epsilon, and then it's much easy to see what delta should be. But here I need to do a little bit of work to see what delta I should be picking. So this is a tricky exercise, I admit. But okay, now that we have the delta, I think you can solve it yourself, right? Because this is now, once we have the delta and we have the estimate like this, we can just solve it in the standard way. You can also look at the exercises on ClickUp, at the solutions to the exercise on ClickUp, where it's spelled out explicitly. So maybe try this yourself, and if you don't figure it out, just look on the answers to the exercises on ClickUp. Okay, any questions about this? Yes, Miss Bandiswa, do you have a question? You raised your hand.
Yes, sir. I just want to ask, basically, like, it seems like you need to know certain tools in order to manipulate some of these limits into getting the answer you're looking for. So, just based off of the examples given in the textbook, they don't cover all of the tools that you need to know. So then how do you know what to use and when? Because in some of the examples you can tell you need to know the reason for removing certain things or for changing things a certain way. So
Yeah.
I'm really struggling with that.
No, I understand. Okay, so yeah, so here, Okay, again, I want to iterate that this is a difficult question and that it's not an embarrassment if you're not able to solve this. And this is because, okay, so these tools that I've used over here, namely the monotonicity of the exponential function, and so on, these are tools that you've had in the first year, but the difficulty is the fact that you need to see to apply them here.
Yes.
And in any question, you may be asked to use tools that you've learned in the first year. So in general, that's a difficult question to answer. But what I will say, which is maybe some consolation, is that these questions are quite difficult, and the exam questions are usually a little bit more, how shall I say it? We usually do not require that they're a little bit more standard in the sense that, yeah, okay, I'm struggling with explaining this a little bit, but the point is that, okay, this is very difficult exercise because it's difficult to see why you should take these steps, and that sort of comes with experience. So it's a good practice exercise, and if you can do this yourself, then you can be really confident. But the exercise in the questions in the exam are more likely to be a little bit more standard, where the techniques that you should be using are ones that should have been covered already in other parts of in the yeah, they should have been covered in the lectures and/or assignments and/or worksheets
Okay.
in a more structured way. Okay,
Okay.
I'm struggling a bit with expressing myself, but hopefully you understand what I mean. That
Yes.
this is
Yes. I do.
that the exam questions will likely not be as tricky as a question like this.
Okay. Thank you very
Yeah,
much.
does that make sense? Okay.
Yes. Thank you.
Yeah. Okay. Any other questions about this exercise? Yeah. Do you have another question, Bandiswa?
Yes, sir. I had asked about exercise 2.4, number 1.
Yeah. Okay. Let me ask Dr. Olaf. Are you back or?
Let's see if I'm back. If you can hear me now, then hopefully the computer is decided not to act up anymore.
No, it's I can hear you perfectly. So
Oh, that's
maybe if
good.
you could try taking over from here.
Thank you. I will do so. So let me just be clear, Mandiswa. So you are talking about exercise 2.4, number 1. Did I have that correct? Okay. I'm going to clear the screen. Thank you for this explanation, Dr. Wortel. So we're now looking at 2.4, number 1. Okay, we simply have to use the limit laws to prove, in this case, that the product of a function of two continuous functions is continuous. Yeah, let's do the function h1 there. So yes, given, I think I can do this with text a little bit. It makes it clear. Given, we've got a function f. F and g are continuous, and they both are functions of two variables from R2 to R. And yeah, well, let's add the other one. C is a constant, it's a real number. And you have to prove that the function show, for example, that H2, which is equal to C times F, what I wanted, come on, H2, which is equal to C times F, is continuous. Okay, so what the way that we start this proof is as follows. Come on. My typing is also bad, but at least I think you can read it easier. Okay, we choose an arbitrary point A, B, be any point in R2. Okay, what does it mean if we say that f is continuous at that point? F continuous at the point AB means the following. It means that now I have to write in any case. I'm not going to get away there. It means the following. It means that the limit when xy tends to AB, the limit of f at xy when xy tends to AB is equal to what? It's equal to the function value at that point. That's just plain the definition of continuity. Okay? Now, if we apply the limit laws, what do we know about the limit of a constant times a given function? We know that that limit will be the constant times the limit. So the limit when xy tends to AB of c times fxy, according to the limit laws, is equal to c times the limit when xy tends to AB of fxy, f at xy, and according to what we have in the first step there, this is equal to c times f at AB. Okay. In total mean, if the limit when xy tends to AB of c times f at xy is equal to c times f at AB, that is exactly what we need to be able to say that the function c times f is continuous at AB. I'm using terrible shorthand here just because it's difficult to write. Okay, and that's the total sum of the proof. And the other one works exactly the same. If you start with what does it mean to say that f and g are continuous, you get the limit when xy tends to AB of f xy is equal to f at AB, and the limit when xy tends to AB of g xy is equal to g at AB. What will happen to the limit of the product? You simply apply the product rule for limits, and you will get the conclusion. I hope that's clear enough, Pandiswa. Are there any questions about this? You are welcome. Remember, with all my logging off and logging back on, I have lost all the questions that were posed. So if any of you students still have a question that has not been addressed, please just repose it so that I can see which ones I need to still do for you. Dylan, yes, I think in a certain sense we always use the definition, except that if you simply want to establish for yourself if a function is continuous, you're not going to necessarily prove the limit from first principles. If you follow what I'm saying, remember that we have methods of calculating limits. We went to great pains to show that, for example, if you look at polynomials, they're always continuous and it's very easy to find their limits. by normally, if it's just a polynomial, you can use what we call direct substitution almost. So you're not using the definition per se to prove that the function is continuous. That's something different. If you have to prove a function is continuous at a point, then you have to use first principles. But you just want to establish whether it's continuous, you try and calculate the limit using whatever means you have, and you check if the limit is equal to the function value at that point. I hope I've answered your question. I see you saying thank you. So yeah, it's the reversed question is almost easier to answer. How do I know a function is not continuous? Well, one of the things that you need to look for is points where the function is not defined. For example, if you have a function that is defined by a quotient of two polynomials, then you know that the domain of that function will exclude any points where the denominator is zero. And at those points, then obviously the function cannot be continuous because the function value doesn't even exist. The limit may exist, but it cannot be equal to the function value because that point is then not in the domain of the function. I've said a lot of things. I hope I haven't confused you. Great. Thank you, Dylan. Any more questions? We still have plenty of time. Okay, Bandiswa has a question for us on exercise 2.3. Just give me a moment. I'm going to clear the screen so long. And what we're going to look at is 2.3, number 1. So we're looking at this expression. Let's say that f at xy be equal to x squared plus y cubed over x squared plus y squared. Okay, and then you've probably had a look at the notes. What we see here is that if you look at the function value when x is 0, you get 0 plus y cubed over 0 plus y squared. Assuming that y is not 0, you modify this to just be equal to y. Okay, so limit when xy tends to 0, 0 of fxy exists, then it must be equal, because when y tends to 0, this is clearly going to be 0. Okay. Now, they've also suggested there in the notes, if you had a look at that, if you choose epsilon equals to a half and consider delta over 2, 0. So maybe we need to make a little sketch here. Come on. So using epsilon equals to a half. Okay. And if you look at any delta, going to look at any point of this form where delta is. Okay, so where do those points live? We want a contradiction here. So we're going to say what happens to these points when delta over 2, if you look at a point to 0. So what happens to those points? Let's have a look. The function value at a point like that is going to be equal to, can you all see that? The y's are 0, so y cubed is 0, y squared is 0. Squared over x squared just gives you a 1. Okay. So at all of those points, to be impossible for the function value to be less than delta over 2. Less than epsilon, which is equal to a half, because the function value is all to 1. So even if I have, in this case, if the distance between my point delta over 2, 0, minus, said the limit must be 0 when xy tends to 0. If that is less than, well, in this case, it will just be, that distance will be delta over 2, and that will be less than any delta positive that I use. Even if that is true, I still have that the distance between delta over 2 minus 0 going to be 1, and that is not less than epsilon. That is prediction, so the limit does not exist. But different, remember, there was a nice video made also on how to prove that a limit exists. In that case, we use theorem 45 most of the times. The difference with this problem was that they said you have to use the definition. So you have to go to first principle that for a certain epsilon, there's no delta that you can find such if the distance between the points x, y, and 0, 0 are less than delta, the function less than epsilon. Here's an example of a particular epsilon you can choose for which you cannot find anything that will work. So that's using the definition. If you were simply asked to show it doesn't exist, you could have used theorem 45, where you either different paths that give you different limits, or you find a path for which the limit doesn't exist. Then by theorem 45, you can say that this limit doesn't exist. I hope I've answered your question. Okay, Nicola Smith has a similar question about the non-existence of a limit, and she wants us to have a look at the steps that were followed on page 51. Just give me a moment to have a look at that. Yes, Nicola, it's very much the same principle as what we've just done in this example, where you choose certain values that give you an indication that the limit, in this case, on page 51, if you look at line number 2.f, you conclude that when x tends to 0, the limit of f at x is equal to 1. So that means that if the limit exists, the limit should be 1. But then again, if you take an arbitrary epsilon, then for any delta greater than 0, I'm looking now line after 2.27. For every delta, the point with coordinates 0, delta over 2, is such that the distance between that point and 0, 0 is less than delta, but the difference function value at that point and 1 is 1, which is greater than a half. So there's no that will work for this particular epsilon if you choose your equal to a half again. Okay, I hope that helps you. Yeah, you're asking why are the steps followed? Well, the definition says that for every given epsilon, you must be able to find delta such that something's true. So what is the principle that we're using here? We do that there is a particular epsilon for which you cannot find that will do the trick. That's in simple language, if you follow me. To show that the limit, you must be able to show that for every epsilon that you can think of, any number, you must be able to find a suitable delta such that whatever it needs to be. If you want to show that the limit does not exist using the definition, you must be able to show is one epsilon for which no delta greater than 0 will work. And that's basically what we're doing here. I don't think Bottle wants to add something to that. I don't know if I've explained that very well. Okay, can you still hear me? Are there any more questions? Come on, guys, we still have plenty of time. You're welcome to post more questions. Speak, Mangliswe.
Sir, I'd like to ask question exercise 2.2 number C.
Can I just make sure that I'm going to clear the screen and just correct me if I didn't get it right? I understood that you want to look at exercise 2.2, number 2. Is that correct?
1C.
Sorry, 1C.
Yes.
Okay. Come on, that. So this is the limit that we need to look at. The limit where xy tends to 0, 0. Okay, have I got the right problem? Whose question was this? This was AI. Okay, now the hint that was given is you should first show. Okay, I've got the right problem. That's a good start. The first thing that you should is that if you call that fxy, you must show that the absolute value of fxy minus 0 is less than equal to the distance between xy and 0, 0 squared. Okay, so that's the first thing that you must try and show. Okay, well, let's start with that and see if we can prove this. So take absolute value of f. It's going to absolute value just of x squared plus y squared over y squared plus 1. Can you see that this is less than or equal to x squared plus y squared. Why is that true? Because if you look at the expression here, let's get some color going here. If you look at this, then you can see that the denominator is clearly greater than the numerator. In other words, that is than or equal to, it's a fraction of y squared, actually, that's what it means. So that, and the absolute value of x squared plus y squared, and go back to the blue color, then this you can see is just exactly equal to the norm of xy minus 0 squared. Okay. That's the first thing that you have to note to be able to do this problem. Okay. From there on, I think the rest is actually covered. Notes of the solution. Okay. The only trick was to see the first part. Okay. For the rest, you can just see the notes on the solution. Okay. Let me just make sure, Bandis, why you're happy. It looks like it. You said thank you. Nicole, some numbers here. I'm not just sure which. Is it exercise 5.3? Hey, Nicola? 5.34a, is there something like that? Have a look. 5.34a. Got it. Thank you, Nicola. I'm going to just clear the screen again. Right. What do we have here? We have, is the region above the cone with the equation z equals the root of x squared plus y squared minus 1, and below the paraboloid z equals to 5 x squared minus y squared. Okay, so obviously always good to have a sketch. Ooh, don't know where that can go. X, y, z. The cone that we have looks like this. It's facing upwards because it's a positive root there. Its intercept with the z-axis is at -1. So there's a cone. And then we have a parabolic facing downwards. That's because of the x squared negative y squared that intersects the z-axis at 5. Okay. And it's looking something like that. Ooh. You can see why I never became an artist, eh? Okay, so the area below the cone, below the paraboloid of the cone. So we are looking at, let me add some color to this. We're looking at that area there. And what you need to be able to this is you obviously need the intersection of these two curves, because that's going to give you a region here in the xy plane. You need to find that intersection, okay? I want that color back, blue. Okay, so yeah, what's the easiest to do this now? Okay, let me. I'm going to start with this equation. Z is 5 minus x squared minus y squared. I've just rewritten this a little bit. And now if I use that, I can get that the root of x squared plus y squared is equal to z plus 1. Okay, so this is 5 minus z plus 1 squared. And then we need to simplify this whole lot. Z is equal to 5 minus z squared plus 2z plus 1. So that's going to give us z squared plus 3z, I hope. That's minus 2z, so that's 3z minus 1. That gives us a 4, so minus 4 equals to 0. And that will give us z plus 4 times z minus 1 equals 0, which means either z is equal to 1 or z is equal to negative 4. Now the z negative 4 is obviously not applicable in this case, because at negative 4 the cone doesn't even exist. So that we have z is equal to 1. Now z is equal to 1, go to whichever equation you want to use. Let's use that one. If I put z equals to 1 in that, I'm going to get 1 equals 5 minus x squared y squared, or you're going to get x squared plus y squared is equal to 4. So that's the equation of that circle there. X plus y squared equals 4. So I think from here on it should be quite simple to what was the express the volume. The volume of the region is always given by the integral of the top surface minus the surface over the region that you have, and the region that you have is just this region now. You can find the in the notes. Okay, the trick was just to find how you find that intersection, that circle there, and this is how you do it. Does that help? Great stuff. Nicola also had 3. Where is 6.3? Number 6C. Okay, can I clear the screen here? No problem, Nicola's happy there. So we're now going to look at it's not sufficient to prove that the function is continuous. To be able to show that the difference between f at xy and f at a is less than can be made less than any epsilon greater than 0. Well, particular one. It's just a particular value for epsilon. That's not good enough. What about epsilon equal to a quarter, epsilon equal to 1/8, etc., etc. So the answer is no. It's not sufficient to do that. Not continuous. Okay. Sufficient to show that the difference is less than 1. I think it's sufficient to do that. You must be able to, rather than show that regardless of which delta you choose, the distance between the absolute value of f at xy maybe is greater than some epsilon. If you prove that it's greater than 1, regardless of whatever delta you choose, that would be good enough. In the 2 examples that we've discussed, in both cases, we show that for epsilon equals to 1/2, you cannot find a suitable that will be such that if the function values are less than, if the points are close enough, sorry, I got interrupted there. Let me just repeat that. If you can show that for a particular epsilon delta that will do the trick, then you can say the function is not continuous. But just doing, and that epsilon can have a value of 1, that's fine. In the 2 examples we discussed this morning, in both cases had a value of 0.5, and we showed that for that particular epsilon, you cannot find a suitable delta that will work. That way around, your question makes sense, okay? But then that the distance between f at xy and f at ab is less than 1, you'll that it's greater than 1 for any delta that you choose. That would make sense. I hope that helps. Okay, I want to get back to Nicola's question, which was sequence 3. Number 6. C. Come on. 6.3. Number 6. C. That's the one, Nicola. Yes, I know. Okay, so I'm not going to write out the whole question again. We've got the first octant. First octant means that's where x, y, and z are positive. And inside a sphere with the equation x squared plus y squared equals z. And above the plane with the equation x plus z equals 1. So yeah, the sketch looks something like this. We've got a sphere with radius 1. But we're only looking at the inside the sphere in the first octant. And then we've got a plane. Okay, so this one is x squared plus y plus z squared equals 1. And we x plus y plus equals 1 as well. Okay, so that plane, if z is equal to 0, got the equation y is 1 minus x. So it looks like if sorry, that was when x was 0, you get z is 1 minus y, and if y is 0, you're going to get z is 1 minus x, and z is 0, you're going to get that. Okay, so there's your plane. It has an angle of 45 with the positive with the xy plane basically. We want to be inside the sphere and above the plane, and we have to be in the first octant. And we want to use spherical coordinates. Okay, so if you have to use spherical coordinates, Yeah. What is the easiest to start with? The easiest to start with is probably phi. Ooh, also not so easy. Theta is quite clear. I think theta is quite. If you're working in the first octant, theta must lie between 0. Okay. Remember, this is where we measure theta. It goes from the x-axis up to the positive y-axis. So theta will be between and pi over 2. You now need to find the equation of u. That's quite a lot of calculations that you need to do. You need to find the equation of this plane, because what's going to happen here is your phi to go from 0 and it has to go up to exactly this plane here. If I can draw it like this, it's going onto the plane there. Remember, that plane has an angle of 45 degrees there with the xy with the xy plane. Phi that plane goes all the way up to here. So phi will also go from 0 to pi over 2. Right, so finally, you have to say what the parameters for rho is going to be. Rho, how do you pronounce it? Rho, well, it ends, remember, it's inside this. So it has to end at 1. What we need here is, where does it start? It starts on plane here, on that plane, where you have x plus y plus z equals 1. You have to translate this equation, x plus y plus z equals 1. You have to translate that into spherical coordinates. Okay. So you're going to substitute all the values for the spherical coordinates here. You will find that you have rho as a common factor. Left here will be something like this: sine of phi cos theta plus sine of phi sine of theta plus cos phi. That's equal to 1. So solving for rho, you'll get rho equals 1 divided by whoop, that long thing there. So this is your question mark. There's your question mark. What? That long expression. Sine phi cos theta plus sine phi sine theta plus cos. Okay. Yeah, the rest you can do on your own, also with the help of the solution that's provided. Nicola, are you okay now? Great stuff. I hope all the questions now. We still have a bit of time left if you have more. I see most of the students are ready, but you are still welcome to pose questions. I'll give it another minute or so. If you have further questions, we can end the session, but I don't want to take away an opportunity for you to ask. So if you still have questions, please post them. Okay, I'll give it one more minute for questions, and if there aren't, I'm going to end the session. Dylan, I see your question. You want to know when tomorrow's session is. I am not sure, but I'm sure there's an announcement on ClickUp. Just have a look. Unless Dr. Wortel wants to confirm what the time is. Dr. Wortel, are you there?
Tomorrow's session is at 3. 3 o'clock.
Thank you. Okay, but I think I'm going to end the session now. There weren't any other questions regarding the material. So thank you for all of you that attended. Thank you for the questions and your participation. And keep on working hard, prepare well for the exam, and I trust that